Hello and welcome back to Calculus2. We are done with the chapters 8 and 9. We are done with all the derivatives and all of the integration and everything else, and it's time to start something completely new. Discrete mathematics, something you're not used to, something you haven't most likely dealt at all with before. And we'll have to have some rules of survival here, because you either end up being amazing in this stuff or you are absolutely abysmal, and that depends on obviously the level of study time you put into all of this. We also need to think about exam 2, which hopefully can happen sometime next week at any point. Well, I say hopefully, because we only have about a month left, 5-6 weeks left, and then there is a final. So we still have exam 2, exam 3, and then the final exam, and we I hope we don't want all of that to happen in the last week or something. So, a whole bunch of things to think about. I will also point to all the reviews and so on, and we'll have another review once we settle the date. But we can literally have it on any 2-day kind of deal. Hopefully next week, right? I will post the announcement with a question in Canvas, and then hopefully you guys will answer and participate to try and figure out. We'll have the quizzes on my MATLAB, and then I'm working to actually merge exams into Canvas, because my MATLAB has proven to be unstable now because of all of the use there, experiencing a lot of users and so on. So it's been very difficult time for them. So maybe we can make it a little bit better if we just move the exam out of there. All right. So 10.1, 10.2 talk about sequences, and then the rest of chapter 10 is going to be on series. Chapter 11 power series, and then chapter 12 3 sections on parametric equations and polar coordinates. So we have quite a lot of stuff to look at. This is technically, now we are entering that third last part of Calc 2, where you learn about discrete math, in this case sequences and series. Now, in the book, they have the overview. They talk about series as well in section 1. I'm going to avoid talking about series and talk in general about series in section 10.3 when I introduce basic series, and then for the rest of the chapter will be series. So let's focus on sequences only, and we'll deal with series when we get there. So we're going to start with the definition that a sequence is an ordered list of numbers. So it's more specific than a set, right? Set is not ordered. On a set, you just, throw items in and you have a set. Sequence is very particular because it has the word ordered. And it's ordered using the natural counting numbers. So let's go blue, I guess. I'll point right. We use n, right, which are natural numbers. So sequence is denoted as an. The book loves k, so they use k a lot. I use n a lot. It doesn't matter. You can use any letter you want. I've seen I, J, M, N, K. I've seen L as well. So a whole bunch of different values that we use to denote whole numbers, the counting numbers. I'm just going to use N for most part, but then we'll use K's as book as well, and so on. So AN is going to give us this list of numbers, the set of numbers. A0, which is the first term. A1, A2, A3, A4, going on forever. This, and I will also, this is also important, can be finite or infinite. So it will depend on the situation. So what I can do is I can go to the classroom and arrange all students by height or by age, or by from smallest to largest or largest to small. It doesn't matter which way we order, right? But it's important to order so you know which number is first, which one is second, which one is third, and then we go in either in the increasing or decreasing. We can do height, we can do weight, we can do age, we can do size of shoes, right? But we try to find those characteristics that will really be different. So we don't want to, I mean, you could have everyone to be the same height or the same weight, but it's highly unlikely that we're going to have that. So we can just, order people in that sense, and we would have some kind of a sequence. So sequence is literally nothing special, right? It's just a list of numbers. That's all it is, list of numbers. And that list of numbers could be represented as the list itself, or you can have a formula which would generate that list of numbers. So we can list the members, or we can have a formula to generate them. Those are, or you know what, we can list the, I'm just going to use the word, list the terms of the sequence. So instead of word members, terms. All right, cool. So what is term? Each one of these terms, right? Those just the members of the sequence. Examples. So I can give you a sequence 1, 1/2, 1/4, 1/8, going on forever. So this is if you list them. You can also say AN equals 1/2 to the n. One over 2 to the n. And that would be with the formula. Both of these are the same. Start with n equals 0, and then 1, and then 2, and then 3. And you are going to see that you're getting the same thing as above. 2 to the 0 is 1. 1 divided by 1 is 1. That's the first member. Then, when n is equal to 1, you get 1 over 2 to the 1. 2 to the 1 is 2, so 1/2. And then you have 2 squared, which is a 4, which makes a quarter. And then 2 cubed, which is, right, gives you 8. And it just goes through like that all the way And we now have these two ways to represent our sequence. Now, the sequence can be finite, or it can be, as I said, infinite. What you see here is the example of infinite sequence, right? Because I put those 3 dots. And I also, for the formula, I put the 3 dots in the n part, meaning that you will never stop generating terms, because I put the 3 dots on the n, and n is the one that plugs in the value to compute the next, right? The next term. So if I let the number of n's to go to infinity, well, you will have a corresponding number of terms. So if n goes to infinity, then the an, or the number of terms, it will also go to infinity. So that will be infinite sequence, right? But I can also say, all right, I'm interested in a finite sequence. I want just, like in a classroom, 30 students. So it's limited to 30. If I arrange everyone by either body, height, or weight, or whatever, right, it's going to be finite, right? Because at most 30 people would be in the classroom. So 30 students, right? So the sequence can be finite, could be infinite, and application, right, will drive which one you need. Now, finite are always less interesting than the infinite ones, because the finite ones, you just see all of the members, you can interpret the data, you can put that in a, even if it has 150, values to it, you can still arrange that in Excel in a chart, let's say, and have some kind of, representation of that sequence. So in terms of the data, so, you can do statistics and everything else. But the idea is that, when you have a finite, sequence, right, there's not that much, right, interesting things happening. But for the infinite ones, right, we would like to know things. So we'll see what are all of the cool features and things that we can figure out. So now we have our sequence, and it's just an ordered list of numbers. Now, formulas which generate our sequences could also be recursive, and also known as a recurrence relation. So when I have, let's say, an example, an equals 1 over 2 to the n, this would be called explicit formula. So explicit formula. And what that means, we need values of n to compute. So that's what we need. But now there is another type which is called recurrence relation, which can look like this. There we go. So something like this would be called recurrence relation. And I will just say we need, in quotation mark, old terms to compute new terms. Now, I hope that something like that would be will make sense. So if your n is, let's say, 3, then this is your A3, this is your A2, and you will be able to compute A4 for n equals to 3. So you have to use A3 and A2 to make up, in this particular example. I mean, oh, Fibonacci sequence. There's the one that you are familiar. Right? So, example. I mean, this is example here, but you are all familiar with the Fibonacci sequence. Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, and then I got bored. So how does this work? Well, 1 plus 1 gives you 2, and then 1 plus 2 gives you 3, and then 2 plus 3 gives you 5, and then 3 plus 5 gives you 8. So as you can see, you always add the two members to, so you add two members, two consecutive members, and that will create the next member. Okay, so how can I represent that in a formula? Remember, what you know, just say it to yourself. Oh, I need to add two terms, two consecutive terms together to create the next term. So if I am adding an plus the next term an plus 1, that would make the next term an plus 2. So think about this. This is your A0, this is your A1, this is your A2, A3, A4, blah, blah, blah. So what is A2 equal to? It's A0 plus A1. What's A3 equal? Well, it has to be A2 plus, well, let's go A1 plus, keep 1 plus 2. What's A4? Well, it has to be A3 plus A2. Right, so it's always two previous terms added create a new one. So this is one way. Now generally we like to either put this one to be n plus 1. So I'm just gonna say, or you can have an plus an minus 1 equals to an plus 1. That's also a formula for Fibonacci sequence, because, you know, check it. Say n is equal to 4. You have your A4, you have your A3, and together they make A5. Sure, 3 plus 4, A3 plus A4 is A5. Those are, A3 is just the location, right? It's the name for the term. We don't know what its value is. Now, those of you who are in computer science, you're already seeing why this is so important, right? One thing is the name, and the other one is what variable is stored inside, right? So we have indexes that are dealing with the name of the term, right? Position of the term, location of the term, whatever you want to call it. And then you have the an plus 1 actually, which is the value, right? So from this sequence over here, we would say that A4 is equal to 5. So it's a fifth term, right? Because you have a 0 as well. It's a fifth term in the sequence whose value is 5. So how much is A6? A6 is going to be 8. So that's it's the seventh term in the sequence, and its value is 8. So you are looking at the whole thing over here like an x, right? Except x is not just one value, it could be, right? It changes. It's a little bit strange analogy. It's not the same by a long shot. But you need to understand that this would be like x plus y equals z, okay? So we're not learning any special things here. We're just trying to put things you already know in a perspective. And we're going to call it sequences. We're going to use them later on to build series. Well, that's next time we have a lecture. All right, so we can do that for Fibonacci sequence, or you can also say, how about an minus 1 plus an minus 2 to give you an. That's fine as well. Like, all of these are fine. All of them are fine because you always have two consecutive ones. Look, n and n plus 1. They're consecutive because n is 100, then the next one plus 1 is 101. So they're consecutive. Same goes here. You have some an, and then you have a term before that one. It's okay. So if you have a5, then you have a4 as well, right? Because if n is 5, 5 minus 1 is 4. Cool. Let's take a look at some sequences. An is equal to 3n plus 6. What can you do here? Well, you can list the terms. Note there is no, in this case, right? There is nothing to say that it's finite. This n by default is infinite if you don't say, okay, we're not going to count past this number, so and so. But no one said that for this problem. So it's going to be a sequence that has infinitely many terms. And then you can start listing those. So an is equal to, and what do we have? The first term is when it's 0, so it's 6. So this is when n was 0. Then n switches to 1. Well, when you plug 1, you get a 9 over here. Because 3 times 1, right? Because n took value of 1. Your n can only be counting numbers, so don't attempt to put fractions or decimals less than 1 or something like that. You can't, right? It's 0, then it's 1, then it's 2, and there's nothing in between. So next one is 3. 3 times 3 is 20. No, 3 times, no, 3 cubed. 3 times 3 is 20. No. 3 times 3 is 9. We should end this now. We should end this now before I say something even worse than that. So 3 times 3, yes. Why 3? See? I'm already losing it. And it's 2. For the third term. Yes. We started at 0, then it's 1, then it's 2. Okay. 3 times 2 is 6. 6 plus 6 is 12. Holy nightmare. Now we get to the dreaded 3. 3 times 3 is 9 plus 6 is 15. Let's do one more. N equals to 4. That's the fifth term. That's 12 plus 6, 18. And then I'm going to put 3 dots to signify that this never, ever, 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 ever ends. It's infinite. Cool. So now, let's go with the next example. Try this one on your own for a couple of seconds. So you can call them AN, BN, CN, whatever. Just like you have X, Y, Z, and so on variables, right? So AN can be, doesn't have to be AN. Could be BN, could be CN, and so on. So let's say that BN is given as n over 2 n over 2 to the n minus 6 need first 3, let's go with 4 terms. So try this problem. Try to list on your own, right? Try to list first 4 terms. Alright, so you are listing the first 4 terms. Let's go. Bn is, well, the first term we're going to use is 0. So we have 1 minus 6, that's negative 5. So we have n equals 0, 1, 2, and 3. That's it. That's the first 3. The first 4 terms. So that was 0. Now we plug in 1. We get 1/2 minus a 6. Right? So that's negative 11 over 2. I hope. When you plug in 1, you get 1/2 minus 6. So that's 12 halves. And then, yeah. Okay, cool. The next number we plug in is 2. 2 divided by 2 is 1. So now we get negative 5 again. Because 2 divided by 2 raised to the 2 minus 6. That's 1 squared minus 6. That's 1 minus 6 is negative 5. And number 3. Right? 3 is going to be 3/2 to the n. So 3 to 3, that's a 27 over 8 minus 6. That's a 48 over 8. And that's going to be 21 over 8. So negative 21 over 8. Dot, dot. No, dot, dot, dot. I asked for the 4 terms. Done deal. You close this set. You close this set because we are done, right? List 4 terms, you listed 4 terms. List first 4 terms, same problem. Well, similar problem. Cn is equal to Cn minus 1 plus 2Cn minus 2. C0 is 6, C1 is 2. You have to be given these start values so that you can compute the next one, right? So let's see what are the first 4 terms for this. This is the recurrence one, right? So you are using old terms to calculate new terms. Okay, so we are going to plug C2, which would be C1 plus 2C0. C1 is 2 plus 2 times 6, we get 14. C3 is going to be C2 plus 2C1. You are using two previous terms. C2 is 14 plus 2 times C1, which is 2, which is 18. And very good, Rory, you got it. We have our sequence over here, 6, 2, 14, 18. There we go. So once you have either explicit formula or recursive formula, you should be able to quickly figure out what the members of the sequence are. Now, the trick is to go backwards. You see, in nature, right, in sciences, you usually observe the sequence and then you want the formula for it, right? Because we don't know formulas and then match the nature to the formulas. We observe nature, we do measurements and all that stuff, and then we come up with formulas. So let's say you observed nature and you came up with numbers -2, 5, 12, 19, right? What's AN that generates this? So there are tricks of the trade that you can use to come up with this. You can ask yourselves, is this some kind of a linear growth? That meaning that is it always the same number added between all of the numbers? And the answer is yeah, in this case, because this is the cheapest problem you can possibly imagine. Do you guys see? +7, +7, +7. Right? Excellent. I see the chat. Yes, very good. Very good. So, we are always adding +7. Now, we need to write that somehow. And there is explicit formula and then recurrence. Now, if you can write explicit formula, that's always better than recursive ones, right? It's better for computer science, it's better for everything if you have explicit formula, because you are only computing what is there, right? When you are using recursive formula, you have to call on, right? You have to retrieve or you have to call on old values, right? So it's more work in terms of your time in your calculations, but also more work for computer processors, right? Because they have to recall. So we try to stay away from recurrence if we can help it, and then in some cases you can't, right? So there's no way to write a Fibonacci sequence in any other way other than recurrence, right? So we're stuck there, right? We have to use it. Now, this particular problem, we can do both ways, right? We can do both ways. So I am going to show both ways, but then again, we want to use the explicit one if we can, and reserve the recurrences only when you absolutely must use them. So what do I have so far, right? It's clear that I have that an is equal to blah plus 7, right? To generate the next term and next term. Now this needs to be some function of n. And if n starts at 0, we have to figure out what goes, right, what goes in a box. So can it just be n? Well, no, it can't, because then the first term would be 7, the second term would be 14, and the next term, right, would be 21. So, and that's not what we have. So it can't be n. But it can be n minus 2. Right? Because if your n is... Oh, Rory figured it out. I'm trying to... Yes. Very good, Rory. Yep. Well, I have to build up to that, man. Because usually this is where people start thinking, I just add 7, but it's actually multiplication by 7. Yes, very good. We will discover that in the next step. All right, so Rory kind of killed it for everyone, so I'll have to abandon this explanation. But yeah, you can do it with a plus 7, right? Even though it's plus 7 for each term, right? It's actually the slope equation, right? It's the slope equation. So it's going to be 7n minus 2. And let's think about it, right? How much is when n is equal to 0? When n is equal to 0, you get 0 minus 2, it's negative 2. Excellent. When n is equal to 1, you got 7 minus 2. 7 minus 2 is 5. When n is 2, you got 14 minus 2 is 12, and then 19, and so on, so it works. Perfect. Something like this would be called geometric progression, and all of the formulas would look like y equal mx plus b, right, which is linear. So now that you see that this formula actually doesn't use plus 7, but you do have plus 7 here, where do we actually get that formula with the plus 7? You get it in the recurrence. So recurrence relation is the one, let's go green, I guess. Maybe I should just box this one and say explicit. Come on, tablet. Tablet is really slow now. Explicit. What is this? All right, now, where's your plus 7? Your plus 7 is going to be the next term is equal to the old term plus 7. And we are starting at a0 being negative 2. You have to include this. And that will be your recurrence relation. Same problem, two different solutions. Now, explicit form is not always possible. All right, let's take a look at a little bit spicier case here. Let me see if I can find something. Hopefully, I can. Actually, I should make one up. Let's see what they have in homework. Here's another easy one. 13927 81. What's AN? That one should be obvious. I'm going to make one up while you guys are thinking about this one. Yep, very good. 3 to the n. Straightforward. 3 to the n. When n is 0, 3 to the 0 is 1. When n is 1, 3 to the 1 is 3. And then you get your 9, 20, 2, 3, So 3 squared is 9, 3 cubed is 27, 3 to the 4, 81, so on. So that's cool. All right. Ready? We have 0, 1 quarter, 3 quarters, 7 quarters, 15 quarters, 31 quarters, and so on. All the computer science people in the class are now, yes, finally, no integrals. Yeah, no integrals until 10.4, then integrals again. So this one is not easy. Now let's learn some tricks. I was hoping, let's see. So the first obvious thing is that we have divided by 4 everywhere. So we're going to take a look at divided by 4. So we're going to have something. Well, let me actually put here, what is AN? Right, that's the question. So I can put over 4 on the first term. That's okay. And what I see is that I have something divided by 4. So that's how much I know right now. That AN is equal to something divided by 4. That's how much I know. And I also want to start my n at 0 and shoot 1, 2, 3. Right? So I have to figure out what goes in that question mark box. Right? So that's where we start. We start by writing what is obvious. And now we have an issue on dealing with 0, 1, 3, 7 and so on. So 0, 1, 3, 7, 15, 31, right? And the question is, does this look like any of the famous sequences which we would use in discovering these, right, with the patterns, what the AN is? Well, it doesn't look like any. Now, by the way, what are our basic sequences? I'll list them shortly. Actually, no. What the hell? Let's list them now. Basic sequences. Memorize this. You already know it, but so you have your sequence n, which is 0, 1, 2, 3, 4, blah, blah, blah. You have your 2n. Hey, that's all the even numbers. You have your 2n minus 1 or plus 1. That's your odd numbers. Then you have n squared. So you have 0 squared is 0, 1 squared is 1, 2 squared is 4, 9, 16, 25. Then you have your n cubed, which is 0, 1, 8, 27, 81. No. 2 cubed, 3 cubed, 4 cubed is 64. There we go, 64. But you also have 2 to the n. So 2 to the 0 is 1, then 2, then 4, then 8, then 16, then 32. And you have 3 to the n, which is 1, 3, 3 squared is 9, 2 cubed is 27, 81, going on, right? So, what do we do now? Well, is any of these close to what we have? And the answer is yes. Two to the n. 2 to the n. Oh, there you go. David got it. Good job. Good job, good job. You have your 2 to the n, and then you subtract 1 from 2 to the n, and then you divide by 4. Mark is correct as well, but you would have to start counting at -1, right? No. So, if I am to add 1 to these, they work out. So if I go +1 on each one of these, then they work out to be 2 to the n. Which means that I need to subtract 1 from 2 to the n. So what's the answer? The answer is an equals 2 to the n minus 1, everything divided by 4. Ta-da! And there is this alternating sequence, which is -1 to the n, or -1 to the n plus 1. You can also have that depending on where you're going to put this. So, -1 to the n is when n is 0, we get 1. When n is 1, we get -1. And as you can see, it alternates between these. Now, this is important because a lot of stuff alternates. You have alternating currents. Right? Polarity switches 60 times per second. That's how often it changes. So we have to be careful with these. They show up. I see one of the problems in the book is asking you for AN, and all they give you are these 5s. That's all. So what do? Well, I say, oh, I have -1 times 5, +1 times 5, -1 times 5, and so on. So I can factor out 5 and just have -1 to the n. Now, we are still not done, because I can't have n. I have to have n plus 1. Because my first term needs to be negative. You see, when n is equal to 0, right? If n starts at 0 and goes through, then -1 to the 0 would be +1. And then +1 times 5 would give me +5. I need -5. So that's why I make the first value for n to be odd, and that would keep the sign. So now you have -1 raised to the first power, where that's just going to be a -1, and then -1 times 5 is -5, which is the first value in our list, in our sequence. So, alternating sequence, right, would switch these signs, and it will alternate between positive and negative, and positive, negative, and positive, negative, and you just have to be careful whether you get to use, right, n or n plus 1. If I started my counter at 1 rather than at 0, then I would have to put n over here, because then the 1 would be the first number to plug in, and you would have -1 to the 1 because you're looking for the negative value in the first spot. So we just need to be a little bit careful, but it's all doable. Now we're going to take a look at terminology, right? The words, which is mainly from 10.2, and that will wrap up our talk about, well, no, we have the test and all this kind of stuff, but once we are done with 10.2, then we are done for the sequences. So let's go and take a look at the next concept here. And I'll start with the graph of the sequence, then I will go into test for the sequence, then I will go into terminology, So graphs. So you are used to XY graphs. And you extensively use them throughout your education. But now you don't have X and Y anymore. And X is no longer even a continuous, right, value. Now it's discrete. You know, the difference between the continuous and discrete is huge. See, your height changes continuously, right? So you had certain amount of inches in length, right, when you were a baby, and now you are whatever amount of inches tall, but that's going to be a huge difference, right? So let's say someone in the class is 6 feet tall, right? 6 times 12, 72 inches, right? So that's growth, right? You became way taller than what you were when you were a baby. But then that growth happened continuously. You had to go through all possible heights, right, between the two numbers. You had to hit every single one of them at some point in life to get where you are right now. That's continuous numbers. But if you are counting eggs, there is not really, 2.3 eggs. And you can go to a store, right, and buy half a dozen, 6 eggs. They have those small packages, and make your breakfast, and you're done, right? Gone and gone. You might be able to convince somewhere in some store someone to sell you 1 egg. Might be, I don't know, but let's say you might be able to. One thing you can do is you can buy half egg, right? So you can't go and buy 15.3 eggs, right? You might be able to buy 15, but you are definitely not going to buy 15.3. So when the units are given like that, where you can't break them apart, if you break them apart to break the unit, right? You are not buying 3.7 cars, you're not going to have 2.8 children, right? And stuff like that. Your height can have decimals, right? The weight can have decimals. So that's not discrete data. So because we don't have discrete data anymore, we don't have the continuous lines, right? Because for us, when we draw the new graph now, and we only can consider the first quadrant over here, I'm going to have an AN, which is the variable stored, but this is my N axis, and N contains only these discrete values as whole units, because you can't go in between them, right? So you can have your sequence of AN is equal to 3n minus 2, and you can go and you can plot this point by point. So when n is equal to 1, you are going to have 3 minus 2, you're going to have 1. And that's your dot at 1, 1. When your n is equal to 2, then you have 6 minus 2 is 4. When n is equal to 3, that's 9 minus 2 is 7. 4, 5, 6, 7. Let me write it in blood. We do not connect the dots. Alright, so do not connect the dots. Because there is nothing in between 1 and 2. Remember, you might be able to get someone to sell you 1 egg or 2 eggs. They cannot sell you 1.7 eggs. That's why we do not get to connect these points. Because if you connect them, then over here somewhere is that 1.7 which we just said we can't have it in our discrete world. Right? So our discrete world, when we have sequences, these explicit formulas, they are going to graph one thing alone, and that is just a bunch of these dots on the graph. And it's not really interesting looking at all the dots, right? But at least we have some kind of graphical representation. Now, there are cool features, right? We'll see that you can, right, that's increasing, right? We're not going to connect them, but you clearly see that the value of AN is increasing as you go to the right. Let's take a look at another graph. Now, this graph is going to be Bn, let's say, is 3 over 2 to the n. Let's say, right? So now we're going to set up our graph over here. We have a Bn, we have our n, and let's start. We can start with n is 0. If n equals to 0, we have 3 over 2, which is 1.5. So that's here. That's 3/2. When n is equal to 1, no, wait, no, that was wrong. When n is equal to 0, we get a 0. Yeah, sorry, we got a 1 here. 2 to the 0 is 1. So we get a 3. Oops. So we get a 3. How about we go 2 units? So that's where the 3 is. Nice. When n is equal to 1, we get 3 over 2 to the 1 is 2, and then that's where you get your 1.5. So now, that's a 1, that's a 2, that's a 3, 4, and so on. 0 was there. So for n equals to 1, we have 1.5, and that will be here. Now, when n is equal to 2, we're going to get 3/4. 3/4 is right here. N equals to 3, that's 3 over 8. So 3 over 8, that's going to be somewhere over here. And finally, n equals to 4, that's going to give us 3 over 16. Now we're getting really close to the n. So we hopefully observe that there is a pattern of going down, right? And over here, we observe the pattern shooting up. So those are observations, but look what's happening here. This one that shoots up is going to shoot to positive infinity. I don't think we need to explain that. That should be common sense, right? We're sitting in Calc 2 right now. So the values will shoot to infinity. But look at this one. This one is going to follow our quotes x-axis. So there's a big difference between them. Not just which one is increasing, decreasing, because we can also have a decreasing graph go to infinity. Right? Oops. Here is the decreasing graph going to infinity. Right? It's negative infinity, but it is decreasing. Right? So the feature that one is increasing and the other one is decreasing, right, is there. That's cool. What we really focus on in these two cases is the fact that the one that grows currently is going to grow without a bound, where the Bn over here falls into the zero. And this is where we're going to use the word converge again. So we would say, by observation, is that Bn goes to zero. Now we say converges to zero. And this gets us to the most important part of, other than the definition obviously, of sequences. And this one says, right, if the limit of n goes to infinity is finite, then sequence converges. If it's infinite, sequence diverges. And we'll have to talk much more about what it means, converge and diverge. But the idea is that it's so simple to get it, right? So here we go with the test for convergence of sequences. Limit n goes to infinity of an can have finite value L. So we say converges to L. Or it could have one of the infinities where we say diverges. Now in Calculus 1, you did 7,000 of these exercises in section 2.5 or 2.4, 2.5, one of those, where you looked at the limits at infinity. I think it was 2.5. Let's test our previous two examples and connect them to that visual output we had. So your AN sequence was 3n minus 2? 3n minus 2. Take the limit. Limit as n goes to infinity of 3n minus 2. Well, how much 3 times infinity? Is infinity. Take away 2 from infinity, you still have infinity. This is infinity, and that's why it diverges. It diverges. The other problem we had, which was 3 over 2 to the n, we'll also use the same test. It's always the same test for sequences. There's nothing else. And you can rewrite this as exponential function with a negative exponent. And now you see that it goes to 0. And you will say converges to 0. If you are not familiar with negative exponential functions, you should be relearning those concepts, because we're going to have a lot of that stuff now. So this is what b to the negative x looks like. It's a decay problem. We call them decay problem. And as you can see, as you are going to infinity, as your x goes to positive infinity, your y drops down to 0, because that's where the 0 elevation is, where the x-axis is. Then you have your 1 and 2 and 3 and -1, -2, right? So you're looking for, remember, limit is technically the y value of the function, right? That's what it is. So as you go forever to the right, it will go down to 0. So that's why this part is 0, and then times 3 is still 0. It goes to 0, right? It's not equal to 0, it goes to 0. Okay, cool. Now, I'm just going to drop these words in here. So I'm just going to drop those words right there. The concept that what we are learning is a joke, right? You just have a list of numbers, and then you come up with the equation for those numbers, the explicit equation, and then you want to see whether it converges or diverges, and all you do is you take the limit of it. Easy, 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 right? Well, if you run into a nasty function, nasty limit, then it's your job to use the L'Hopital rule if you have to, right? L'Hopital rule to solve. So now, since we are in this second part of Calc2, this is where those sections on taking limits are going to be insanely important, because I hope you guessed it right already. Every problem from now on for the next 3 weeks is going to be a limit problem. Every single one is going to be a limit problem of some kind. So you need that L'Hopital rule. You need the ability to take the limits. And I said here in blood, review limits. You need 2.3, 2.5, and I believe it's 4.7 for L'Hopital. Not sure. Or maybe 4.8. It's one of those two. Actually, I can quickly check. $4.7, I was right. Good. Now, the way to practice this, obviously, you go to study plan and you enjoy study plan until you pass out. Because study plan can open any calculus, right? So study plan, you can access 4.7, I mean these 3 sections, and work on it. All right, cool. So now we found out that there is a test for sequences which will tell us whether it diverges to infinity or converges to a particular number. And we also discovered that they can go up and they can go down, right, when we graph them and so on. We see it visually. So we just want to go through a couple of words, like terminology for sequences. Take a look at properties or the laws. And I think, let me just check. That will be it. We are not going to do... Oh, there's a growth rate as well. It's going to be a little bit longer than I expected. Okay, cool. So let's go and talk about laws of sequences. So sequence can either diverge or converge. And when you say converge, we can also say has a limit. Has a limit, right? So that's another one. The other one, no limit. That's the big difference. All right, so let limit n goes to infinity of an be capital A, and limit of bn be capital B. Technically, what this means, an and bn converge to capital A and capital B. I'm going to spell that out. This line means an converges to capital A, bn converges to capital B. That's what it means. Alright, so what are the laws? Law number 1. Limit of an plus minus bn is a plus minus b. So if you add or subtract two sequences, their combined answers from before will combine in the same fashion, and you will have one answer for the whole problem there. Number 2, with a constant multiple. Come on, tablet, you can do it. So limit c times an, well, you get to kick this c outside. You know that the limit is a, so that's what you get. Right, we know this is a. It's defined. That's given. Number 3. The dangerous ones, right? an, bn is ab. So this is something that is true, right? And holds for limits, but it does not hold for product rule, right? For derivatives, it doesn't hold for integration. We have to go around those types of things as we do, right, problems. And the last one, 4, is the quotient. So that's the limit n goes to infinity of an over bn, and that's going to be a divided by b, where bn needs to be different than 0 and capital B needs to be different than 0. By the way, you can have a sequence 0, 0, 0, 0, 0, 0, 0, right? But we have to exclude it here because it would mean that you are dividing by 0, and we know that can be done. So these are the limit laws, and you know, they can help you also with solving the limit. You if you have the, you know, to show convergence or divergence of the sequence. So this would, you know, in some cases these laws could help us find the limit faster. Good. Finally, we get to terminology. Yay! So I should yeah, these are words. They're important. So boom, blood. Number 1. An is increasing if an plus 1 is larger than an for all n. Does this make sense? Yeah. This is the term, and this is the next term. you see that the next term should always be bigger than the previous term, right? So clearly you're going up, right? Number 2, don't get triggered now. AN is non-decreasing. And that's if AN plus 1 larger or equal than AN. Non-decreasing. You see, we're only kicking decrease out, and we can keep the steady flat state. So you can have, let's say, 3, 3, 4, 6, 10. That's why we needed the equal sign, because of those. So non-decreasing means literally non-decreasing, right? So it cannot be increasing, but it does allow for the flat, right? Does allow for that. Number 3, decreasing. So AN is decreasing. If AN plus 1 is less than AN. So the next term, now, the next term is going to be smaller. Every time you see another term, right, it's going to be smaller. So that's decreasing. And, right, to end the symmetry here, N is non-increasing if AN plus 1 smaller or equal than AN. Two more words. 5. AN is monotonic which is, it's either non-increasing or non-decreasing. My pen is giving me trouble. I'm sorry for the lag. I'm gonna reboot the pen. So AN is monotonic if it is non-increasing or non-decreasing. There we go. Now, what does that mean? Well, it's always either always growing or it's always, and even if it stays flat at some point at time, it's okay. Right, but as we progress to the positive infinity for n, right, as we progress to the right, it's either always going up or always going down, and that's what we would call monotonic. And finally, we have the bounded. So AN is bounded above if there is a number, I wanted to write value, but a number, capital M, such that AN is smaller or equal than M. You see the bound. You heard bounds, boundaries. Right now, with the social distancing, you also creating, right, boundaries and so on around your persona. So the bound is think of it as a horizontal asymptote. It's not a horizontal asymptote, but you can think of it somewhat as a horizontal asymptote. It's like a barrier that your discrete values will follow as it goes n to infinity. So when you look at our two examples from before, if this thing doesn't explode while I scroll, what are my examples? There we go. I need graphs. There we go. So this graph over here is monotonic because it's non-decreasing. Non-decreasing means increasing, right? Non-decreasing means increasing, but you have to be careful because the non-decrease can also have those flat parts in the graph. Now, when you look at next one, that one is also monotonic. So that's what the word monotonic means. It's constantly going up or it's going down. I mean, you can have patches of when it's constant, right? But you want it to go up. And bounded. So above, let's underline the important words. And now and/or an is bounded below if there is a number capital N such that your individual ANs are all larger than that N, because again you want your ANs to, well, let's draw a diagram, and let me just underline this. All right, cool. So it's easier for you to think of in terms of continuous functions, and then we can just say, okay, now you just don't need lines, just leave the dots, right? So bounded above, I'm going to mention the virus again. So logistics growth has the carrying capacity, right? And we would say, if this is f of x, I would just say bounded above. See, it cannot cross the value, and that value obviously is what we call carrying capacity, and you find it through limit. There's just so much stuff that you can learn in addition to what we're doing here. So when you look at the logistics graphs like this, you see that once it reaches the carrying capacity, that means that virus doesn't have anyone new to infect anymore, right? Doesn't have anyone else to infect. So the cases and everything would actually stop at that point. But that's the carrying capacity. So what is the carrying capacity? That means that whoever can be infected, and right, so that's whoever can be infected for whatever reason. You didn't social distancing, you didn't do whatever you were told to do, and so on. You didn't pay attention, then you went to the park, I don't know, and played soccer with 5 other people and got exposed, right? So that's all possible. But see, the trick is that at some point, right, it will reach every person everywhere, right? And by that time, hopefully there is a vaccine and, medication and whole bunch of stuff that we don't have now available. But the trick is that this is it. Now, if there was a super virus that is just going to kill everyone, well, this line is still in effect, right? It's whatever the population of people is, right? So there is a carrying capacity. There is that bound that is not crossed, right? The bound that is not crossed. So now we do not have this situation. We have an, we have n, we have our an instead of the function, and instead of all of these black lines, I'm going to have the dots, because I do not have continuous data on the progression of the virus. This could be infected graph, it could be death graph, it could be anything, right? It is, in my eyes, right, discrete dot by dot. I check in the morning, I check in the afternoon, then I check the next day in the morning and next afternoon. I didn't check every split second of every minute of every hour continuously to see the change as it's happening. I'm just taking snapshots, right? Let's say check at 9 and then check at 9 a.m., 9 p.m. every day. That creates the dots, right? Not too many cases, and then cases start rapidly going up, and then when it becomes harder, for whatever reason, for virus to infect people, it starts leveling off, right? It starts leveling off. So the bound is the line on top, which will not be crossed by the function. So that's the bounds, right? You can have one below, you can have one above. Now there is a really cool theorem which says that bounded monotonic sequence converges, and you should just think a little bit about that statement. It's a really cool thing. So it says bounded monotonic sequence converges. Does it make sense? Yeah. Monotonic means it always goes up or it always goes down. Bounded means it has a bound that it cannot cross. So if I have a bound on top, this is capital M, and you have some kind of a an approaching it, well, converges to the bound. M. If you have the bound on the bottom, and then you approach it like that, so that was N, and it's still an, right? This now converges to N. So bounded monotonic sequence always converges. And the last thing that we need to discuss for tonight is the growth rate of sequences. This will help you with limits and will help you in general to think about these things. It's very important. So growth rates for sequences. Some sequences grow faster than others, and we can arrange them in a chart even though we are going to write certain things. So let's take a look at the chart and then we're going to write it out. So I'm going to make a chart of values here. I'm going to populate this chart. So we'll have our n, our 2n, our n squared, our 2 to the n, right? Then we're going to have n factorial, and finally n to the n. So these are the creatures that we want to take a look. Let's go 1 through, I don't know, 6. And then we just populate the values in the chart. So what do I have? (2n). Well, that just doubles all of these. And clearly, right, 2n grows faster than n. In terms of linear lines, like that, right? This is your x, this is your 2x. And 2x grows faster because it's every y value that x has, this one has it as double. So clearly grows faster. N squared. Well, 1 squared is 1. 2 squared is 4. It's kind of tied up. And then 3 squared is 9. Oh, it started winning. 16, 25, 36. And wow, this n squared is really winning against both of these previous, right, cases. So it's faster, right? It grows faster for the same input value. Now 2 to the n. Well, 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. It's kind of either tied up or losing, right? And then 2 to the 4 is 16. So it's still not, right, doing much better. And then 32 and 64, and the next one is 128, where this one is 49. As you can see, it just, you know what, let's add 7, why not? Let's add 7, we can. It just shoots up. Now n factorial. Those of you that forgot what the factorial is, right? This is n factorial is 1 times 2 times 3 times ... and then times n. So what is 1 factorial? 1 factorial is 1. 2 factorial is 1 times 2, that's 2. 3 factorial is 1 times 2 times 3. Well, that's a 6. It's losing. 4 factorial is 1 times 2 times 3 times 4. That's 24. Oh, it started winning. The next number is 5 factorial, and that's 1 through 5. That's 120. Oh, now factorial really took off. Right? Skyrocketed. 6 factorial is 720. Right? And now we need 720 times 7, which is 5040. So even exponential function is struggling. Even exponential function is struggling to catch up. And now we get to the king of kings, n to the n. That's 1 to the 1, which is 1. And 2 squared is 4. And now 3 cubed is 27. And then 4 to the 4. That's 256. Right right here, right on the line 4. It already went up. Now we want to calculate maybe 5 to the 5 and then not bother calculators. Right, that's going to be 3,125. 6 to the 6 is 46,656. And 7 raised to the 7 is 823,000. 5, 4, 3. There we go. Can't even fit, right? So now we're experiencing growth, where we're going to say that ln of some value is the sluggish, slow one. Faster than that are your polynomials, n to the p. Faster than that is n to the p ln n, which grows faster to two polynomials, so maybe p plus q, which is better than your exponentials. I mean, sorry, slower than exponentials, slower than factorials, and I can't fit one more. Really? Which is slower than n factorial, which is slower than the boss. So why am I talking fast and slow? Talking fast and slow, literally looking at the numbers. 5, 10, 25, 32, 120, 3,000, right? So clearly this one rises much faster than any one of the before, right? This one rises much faster than all of the previous ones. So that's when I say slow and fast. So now this helps a lot when you have to deal with limits. See, if I have a limit, n goes to infinity, and I have n cubed ln n divided by, enough threes, divided by 2n factorial, I don't need to compute anything. It's equal to 0 instantly, just by looking at it. Why? Because this one grows much faster than n cubed ln n. And the larger the number in the denominator, the faster it goes to 0. So you have 0. I just said it, right? The faster the denominator grows, the closer to the 0 the whole thing is. Or, let's say you have limit n factorial divided by n to 10,000 as n goes to infinity. By the way, it only works for n going to infinity, but we don't consider anything else in the next two chapters. Every limit is to infinity. So this is equal to infinity, diverges. Right, this one converges on top, this one diverges. Why? This is faster. Now it's faster. So what I'm going to write now is mathematical sacrilege, but it really helps you rip through these problems very quickly. So, limit of slow over fast, right, when you compare the two. Slow over fast is always going to be 0. And limit n goes to infinity of fast over slow is always going to be infinity. These are not mathematical formulas. This is terrible to write, but it's so true and so quick, right? So it can really help you solve many of these limits very, very quickly. And pretty much starting next section, right, 10.3, every problem we touch is going to be a limit problem. So my hopes are that in the next 2 days, in addition to prepping for your exam 2 and practicing chapters 8 and 9, I hope you will go to study plan and practice 5.3, 2.3, the limits, 2.3, 2.5, and 4.7, because we are going to use those as we move on. So please also check the comments, the announcements on Canvas. Get in the discussion if you want to regarding any day. It doesn't have to be Thursdays or because this is now an online class. So your Thursday is your Sunday, is your Wednesday, right? It's just, so if you say, let's have it Friday, Saturday, done. If you say Wednesday, Thursday, done, right? So you can literally, you can discuss it a little bit, in the chat. I know we can't meet and all that kind of stuff, but, there is a chat discussion board once I post the announcement. And then, we'll see whoever wins in comments, I guess. We can do a quick tally or something if you want to vote. Or if you just want me to set the exam for, I don't know, Thursday, Friday, or whatever, and be done with it, we can do it that way as well. I will see you in the comments.